All right, hi everybody. This is David from UCR Supplemental Instruction, here to talk to you again about Physics 40B, and in this topic we'll be talking about simple harmonic motion in a more practical sense, position, velocity, and acceleration. So what have I drawn out here? These are three different slider tracks that we'll be using later on to discuss these three core concepts: position, velocity, and acceleration. And so with simple harmonic motion, as we've learned, it's very regular motion between two places. It's not linear. Everything will follow a trigonometric function, such as sine or cosine. So we're going to talk a little bit about the maximum positions of velocities and accelerations, where they occur, and how you can find them out. So first off, what am I representing here? So in each of these tracks, you can see we have some mass denoted by the red square, moving from one end to the other. We're going to consider this middle section here to be x equals 0, and the position can increase toward x equals a on one end, and it can decrease toward x equals negative a on the other end. And so the other part of this is, of course, why would it move at all? So we're going to say that there is a spring represented here, and that, as you're familiar with springs, due to Hooke's law, the further you displace them, the greater the force that they produce. So, that's Hooke's law, commonly denoted as F equals negative k times x. The negative kind of depends on what direction you're assuming x to be in. In this case, since the spring is acting in two directions, which is somewhat abnormal, but we're just going to go with it, the negative isn't really important. So we have this, and we know this force is what's acting here. So when x equals 0, while plugging this in, we can tell pretty quickly that the force by the spring is going to be 0 because k, whatever that is, times x is 0 and x is 0. And so toward either of these two ends, you can have k times a being a force, or k times negative a. And everything in between will be a linear increase of the force from 0 to ka or negative ka. All right, so that describes our position. So then what we can say about this is that starting here, position is 0, force is 0. As we move, the position, of course, is going to increase until a, and then the force here will be a lot stronger because we're multiplying k by the highest potential value we'll have for x, that being a, at least in terms of magnitude. At the other end, the same thing is true. The magnitude of the force is the same, but of course it has a negative value because we're using a negative value for x. And again, this is sort of where the subjectivity of the negative in Hooke's law comes from. We consider this to be a positive force because it's pulling in the positive x direction. So leaving the negative here might make a lot more sense. Ultimately, as long as you're consistent, things should work out. All right, so the next part of this would be velocity, and so we're going to talk about that here. So for velocity, will it follow the same path where we have some 0 velocity in the middle, or will it be something different? So if we assume that velocity is 0 in the middle, and this is, again, in the midst of any simple harmonic motion, so we're ignoring the initial conditions, and then it increased to some maximum value, just like position, well, first off, from a practical sense, would that make any sense? So, of course, the direction has to change. This is velocity, so direction's important. If we're on one end and moving toward the other, we could have a positive velocity if we're moving from left to right. If we're moving from right to left, we could have a negative velocity. So we know, though, that if we are, oops, that's not what I meant to pull. If we are moving, say, to the left, and we will hit this end and we'll start moving the opposite direction, there's some change in velocity from a negative velocity to a positive velocity. And so because your change in velocity has to be continuous, it's going to have to pass through 0. So in this case, it wouldn't make sense for the velocity to hit 0 in the middle. It'll have to hit at either of these ends where it goes from either negative to positive or from positive to negative. So in the middle, it'll be something else. Now, whether or not this varies linearly, we can probably assume that it's going to be the maximum in the middle. And so we can say that just because, well, if it's 0 at one end, 0 at the other, and it goes to some velocity in between, would that make sense? Okay, well, let's see if we can further rationalize that. So to do this, we're going to talk about the trigonometric functions that describe position and velocity. So for position, it's written out here, a cosine times omega t. It can also be sine. The phase angle is what will change that. We'll get into that in a future video. And then the derivative of position with respect to time is velocity, so we just take the derivative of a cosine omega t. Using the chain rule, we take the derivative of omega t on the inside, which is why it's another omega, and then the derivative of cosine is negative sine, so we get negative a omega sine of omega t. But what's really important here is not that. What's important is that where cosine is 0, for that same value of the argument here, sine will be at its maximum or minimum. So if we say that the box is in the middle here, and for whatever value of omega t we have, cosine is 0 because 0 times a is 0, and that's the position we have marked here. If we plug that same value of omega t into the velocity equation, we'll get either -1 or +1. And so we'll have either negative a omega or a omega. Either way, that is the largest this velocity equation can actually be. So we know then that in the center here, the velocity has to be at its max. And as we saw, it can be either positive or negative. So what that really means is that we don't know, just based on the position, whether or not the box is moving to the left or to the right. So again, to describe that, we'll do that in a future video. And for more clarity, v equals 0 on either end. Okay, so we found that there's kind of like an opposite relationship here. If the box is in the middle, position is 0, but the velocity is at its maximum. And if it's at either end, the position is at its maximum and the velocity is at 0. So we continue. Let's talk about acceleration then. So what is the acceleration going to be at the ends or in the middle? So right now it's at one end. And first off, we can talk about intuitively what makes sense here. So velocity is 0, but acceleration, it depends on the change in velocity, right? So we can't immediately say that acceleration is 0. We do know it's changing though, because it went from positive to negative at the ends, like we said, or negative to positive. So in the middle then, what is the acceleration? Well, first off, it might be even simpler than going to the trigonometric functions if we just look back at Hooke's law here. So F equals negative kx. And force is also equal to mass times acceleration. So if we simplify things a little bit, you can divide both sides by mass. So you have some acceleration equals negative k times x, but also divided by the mass. That's because F equals ma, so I'm just substituting that in for Hooke's law. Okay, so here we can see that acceleration is pretty clearly dependent on the position. So that makes this very similar. So in this case, these two equations are probably going to look very similar, and there's no other arguments here. So if x is 0, just looking at this equation again, negative k times 0 divided by m is 0. So we can assume then for that same position, the acceleration here at the middle is 0. All right, and so intuitively, does that make sense? Well, we're assuming here that the spring is neither elongated or compressed, so it won't be doing anything to this mass, won't be pushing or pulling it. So it does make sense intuitively also that the acceleration here is equal to 0, just like position is equal to 0 in the center. Okay, so at either end, if we follow this trend, just keep plugging things into this equation, what do we have? So intuitively, you can probably guess the way it's going to go. But if we plug a into here, the highest possible value for x, negative k times a over m, will obviously give us either the highest or lowest value, because a or x can't be any higher. So as we move to this position, the acceleration just increases linearly up until here where the position stops, and then it gets pulled back in. And then same is true for the other side, getting pulled toward the center. The spring is always pulling toward its equilibrium point. So the little difference that's here then is that here we consider this to be the positive position of the positive position just rather, but the acceleration is pulling the other direction. So we have this negative value in Hooke's law. So instead of saying that a is equal to a max, the slight difference between this and the position is that it's negative a max here. At the other end, we have positive maximum magnitude. So hopefully this makes it a little bit easier for you to go in and intuitively assess where the acceleration or velocity is at any point. Of course, you can get more specific. You can also take another derivative of the velocity equation to find the acceleration equation, and you also can do things to figure out, given a velocity, the direction of that velocity depended on some of the other information. So that's all for now. We can get more into those specifics in a future video. Hope you learned something, and I'll see you next time.